Our journey begins not with a spaceship, but with a number, c. We know it as the speed of light, roughly 186,000 miles per second. A velocity so immense, it's almost beyond comprehension. But, in the language of the universe, c is so much more than a speed. It is the fundamental constant that stitches the very fabric of reality together. It's the silent architect of causality, the universal law that ensures an effect can never happen before its cause. Think of it as the universe's ultimate traffic law. If you could break it, you could theoretically witness a glass shattering before the ball ever hit it, or receive an answer before you ever asked the question. This logical flow, this elegant progression of cause and effect, is what allows the universe to be predictable, understandable, and even exist in a way we can recognize. It weaves space and time into a single, unified fabric called space-time. Moving through space affects how you move through time, and c is the constant that governs this cosmic dance. This is why the news that broke in September 2011 sent a shockwave of terror and excitement through the world of physics. It seemed a ghostly, almost massless particle called a neutrino had done the unthinkable. After being fired from CERN in Switzerland, it had undertaken a 730-kilometer journey, piercing straight through the solid rock of the Earth's crust to a detector deep beneath Italy's Gran Sasso mountain. And it appeared to have arrived 60 nanoseconds, 60 billionths of a second sooner than a beam of light would have. This wasn't just a small anomaly. It was a declaration of war on the foundations of modern physics. It threatened to unravel everything we thought we knew about the universe, from Einstein's relativity to the fundamental nature of time itself. For a moment, it seemed the ghost in the machine had broken the machine itself. The experiment at the heart of this cosmic drama was called OPERA, or the Oscillation Project, with emulsion tracking apparatus. Its primary mission was to study how neutrinos, these strange, phantom-like particles, could change their flavor, or type, as they traveled. The faster-than-light discovery was a complete and terrifying accident. Deep underground in the Gran Sasso National Laboratory, shielded from the cosmic radiation that constantly bombards our planet, the OPERA detector waited patiently. It was a colossal instrument, weighing 1,800 tons. A high-tech needle in a subterranean haystack, designed to catch the faintest whisper of a neutrino's passage. When the team first saw the data, they didn't celebrate. They were horrified. They understood the magnitude of their claim. Announcing that you have broken the speed of light is like an accountant announcing they've disproven the number 2. It's so fundamental that the error is almost certainly with you, not with reality. With a profound sense of humility and intellectual terror, the OPERA researchers spent months tearing their own work apart. They checked every calculation, recalibrated every sensor, and scoured every line of code, desperately searching for the mistake they were sure must be there. They couldn't find it. So, in an act of supreme scientific integrity, they did something remarkable. They published their findings and invited the entire global scientific community to scrutinize their work, to help them find their error. The world held its breath. If this was real, the implications were staggering. It could mean the discovery of hidden dimensions, a flaw in Einstein's theories of relativity, or a whole new landscape of physics. The mystery was eventually solved, not by some revolutionary new theory, but by something far more mundane, and in a way, far more human. After months of intense investigation, the culprit was found. A single, loose fiber optic cable. This cable, responsible for transmitting the master clock's timing signal, wasn't screwed in tightly. The tiny, almost imperceptible gap created a 73 nanosecond delay in the timing system, making the neutrinos appear to arrive earlier than they actually did. The universe's most sacred law hadn't been broken after all. The revolution was cancelled. But the story of the opera Anomaly serves as a powerful lesson. It is a testament not to failure, but to the rigorous, self-correcting nature of the scientific method. It reminds us that even our most brilliant minds can be humbled by a simple, overlooked flaw, and that the universe, in its elegant consistency, doesn't give up its secrets easily. Having affirmed that nothing with mass can be pushed past the speed of light, we now venture into a realm where the rules seem to bend in the most baffling ways: the quantum world. Here we encounter a phenomenon so bizarre that it famously prompted Albert Einstein to call it spooky action at a distance. This is quantum entanglement, and it represents one of the most profound and mysterious aspects of reality. Imagine you have two particles, let's say, two electrons that are created together in a special way. They become entangled. This means their properties, like their spin, a quantum version of angular momentum, are intrinsically linked. If one electron has a spin-up, you know with absolute certainty that its entangled twin, no matter where it is in the universe, will have a spin down. Now, here's the spooky part. According to quantum mechanics, before you measure it, each particle exists in a state of fuzzy probability, a mix of both spin-up and spin-down simultaneously. It's only the act of measuring one particle that instantly collapses its state into a definite reality. And the moment it does, its entangled partner, which could be in the same lab or in a galaxy, a million light-years away, instantaneously collapses into the opposite state. This influence appears to happen faster than light. Experiments have confirmed this link over hundreds of kilometers, showing that the connection between entangled particles is immediate, defying our classical understanding of space and time. So, have we found our loophole? Can we use this to send faster-than-light messages? For instance, could we agree that spin-up means 1 and spin-down means 0, and then manipulate one particle to instantly transmit a binary message to a distant star? The universe, it seems, has a subtle yet unbreakable safeguard, the no-communication theorem. While the influence is instantaneous, we cannot use it to send a deliberate message. The reason is randomness. When you measure the first particle, you can't choose the outcome. You have a 50/50th chance of getting spin up or spin down. The outcome is completely random. So, your friend on the distant star will see their particle instantly snap into the opposite state. But since they don't know what your random result was, they have no way of deciphering a message from it. It would be like having a pair of magical coins that, when flipped, always land on opposite faces. But you can't control whether your coin lands on heads or tails. Causality is preserved, but only just barely. Entanglement doesn't break the speed of light for communication, but it does hint at something much deeper. A hidden layer of reality, where distance is an illusion and the universe is interconnected in ways we are only just beginning to comprehend. Now, let's leave the world of the confirmed and enter the wild, speculative landscape of theoretical physics. Here, in the abstract realm of mathematics, we encounter a truly mind-bending concept: tachyons. Tachyons are hypothetical particles born directly from the elegant equations of Einstein's special relativity. They are, in essence, the universe's shadow family. While everything we know, matter, energy, people, planets, exists on one side of the light barrier, forever forbidden from reaching it, tachyons are imagined to exist exclusively on the other side. For us, in our world of brudions, slower-than-light particles, accelerating to the speed of light would require an infinite amount of energy. It is the ultimate, insurmountable wall. For a tachyon, the logic is flipped on its head. A tachyon can never travel slower than the speed of light. For it, light speed is the lower limit, and slowing down to it would require infinite energy. These particles would be born traveling faster than light, and would forever be trapped in the superluminal world. One of the strangest properties predicted for tachyons is that they would have imaginary mass, a mathematical concept that sounds like nonsense, but is consistent within the equations. Another bizarre consequence is that a tachyon would lose energy as it speeds up, and gain energy as it slows down towards the speed of light. The immediate problem with tachyons is that they seem to shatter causality. Because they travel faster than light, their existence would theoretically allow messages to be sent into the past, creating all sorts of paradoxes. You could, for instance, send a message back in time to prevent your own birth, the classic grandfather paradox. For decades, this made tachyons little more than a theoretical curiosity, a mathematical ghost in the relativistic machine. However, more recent and highly speculative theories have tried to find a place for them in our universe without breaking it. Some physicists have proposed that tachyons might be compatible with reality if their role is reinterpreted. Perhaps they are not particles that can be controlled to send messages, but are instead linked to fundamental fields that permeate the universe. Some theories even suggest that the field associated with tachyons could be a candidate for explaining dark energy, the mysterious force that is causing the expansion of the universe to accelerate. While no tachyon has ever been detected, their existence remains a tantalizing possibility. They offer a vision of a universe that is beautifully symmetric, with one reality we can see on this side of the light barrier, and another, stranger reality forever racing beyond it. If we can't break the cosmic speed limit, what if we could bend it? This is the stunningly elegant idea behind one of the most famous concepts in theoretical physics, the Alcubière drive, proposed by Mexican physicist Miguel Alcubière in Ix. This is the scientific basis for the warp drive of science fiction fame. The genius of the Alcubière drive is that it doesn't involve the spacecraft itself moving at incredible speeds. In fact, inside the drive's bubble, the ship would be in freefall, floating weightlessly, not moving at all, relative to its immediate surroundings. So how does it achieve faster-than-light travel? Instead of propelling a ship through space-time, the drive proposes to move space-time itself around the ship. Imagine a surfer on a wave. The surfer isn't moving faster than the water. They are simply being carried along by the motion of the wave. The Alcubière drive would do something similar, creating a wave in the fabric of space-time. It would work by generating a region of space-time that contracts in front of the ship and expands in the back. This would create a warp bubble that pushes the destination closer while pushing the origin point farther away, effectively carrying the ship and its bubble of undisturbed space-time along for the ride, because it is space-time itself that is moving and not the ship. The theory doesn't technically violate the cosmic speed limit. The law says nothing can travel through space faster than light, but it places no limit on how fast space itself can expand or contract. Indeed, in the moments after the Big Bang, the universe is thought to have expanded at a rate far exceeding the speed of light. For decades, the Alcubière drive was considered a beautiful but impossible thought experiment for one major reason: it required exotic matter. This isn't just matter that's rare. It's matter with bizarre, physically questionable properties, specifically, negative mass or negative energy density. This kind of matter has never been observed and would violate several known energy conditions in physics. It seemed the warp drive was destined to remain forever on the pages of science fiction. However, very recent breakthroughs in theoretical physics have breathed new life into the concept. Researchers have been exploring new models that dramatically reduce the amount of negative energy required, or even, in some highly speculative new papers, suggest that a warp drive might be achievable without any negative energy at all, using known physics in complex and clever ways. The challenges are still monumental, far beyond our current technological capabilities. But the Alcubière drive has been transformed from an elegant fantasy into a potential, tangible engineering challenge for a civilization far more advanced than our own. It tells us that the universe's rules might be more flexible than we thought, and that our destiny among the stars might not be to break the laws of physics, but to become masters of their application. Deep within the labyrinthian mathematics of Einstein's general theory of relativity, there lie solutions that describe some of the most exotic objects imaginable. We are familiar with black holes, but relativity also allows for the existence of their theoretical cousins, Einstein-Rosen bridges, better known as a wormhole is a hypothetical shortcut, a tunnel through the very fabric of reality. Imagine space-time is a giant sheet of paper. To get from one point to another, you would have to crawl across the surface. But if you could fold that paper over and poke a pencil through it, you could create a tunnel connecting those two distant points, allowing for near-instantaneous travel. That is what a wormhole proposes to do. It could potentially connect to vastly distant points in our universe, or even connect our universe to another one entirely. While traveling through the wormhole, you wouldn't be exceeding the speed of light locally. You would just be taking a much, much shorter path. Like the Alcubière drive, however, wormholes have a catch. According to classical general relativity, any traversable wormhole one you could actually fly a spaceship through would be incredibly unstable. It would collapse in on itself in an instant, unless it were propped open by that same pesky ingredient, exotic matter with negative energy. This has long been the Great Barrier, relegating wormholes to the realm of theoretical curiosities. But a revolutionary new idea is starting to bridge the gap between the very large general relativity and the very small quantum mechanics. It's a conjecture known as equals EPR, proposed by physicists Leonard Susskind and Juan Maldacena. It suggests a profound and shocking connection between two seemingly unrelated phenomena. U stands for Einstein-Rosen bridges, wormholes, and EPR refers to the Einstein-Podolsky-Rosen paradox, which is the foundational paper on quantum entanglement, that spooky action at a distance. The ER equals EPR conjecture posits that every pair of entangled particles might be connected by a microscopic, quantum-scale wormhole. This is a breathtaking idea. It suggests that the spooky connection of entanglement isn't spooky at all. It's a physical, geometric connection through a hidden tunnel in space-time. This doesn't mean we can fly a starship through an electron's wormhole, but it unifies the two great pillars of modern physics in a beautiful and unexpected way. It implies that space-time has a hidden quantum-level topology, an intricate network of connections woven into the fabric of reality itself. If this connection is real, it could revolutionize our understanding of gravity, quantum mechanics, and the very nature of space and time. It suggests that the universe isn't just a vast, empty expanse, but a deeply, fundamentally interconnected system. Let's now consider one of the most radical and mind-bending ideas of all. What if the universe isn't a physical place in the way we think it is? What if, at its most fundamental level, it operates like a vast computational system? This is the core idea of digital physics, which proposes that reality is, in essence, information. In this view, space, time, matter, and energy are not fundamental, but are emergent properties of an underlying network of information processing, like the characters and environment in a hyper-realistic video game, emerging from lines of code. If this is true, it completely reframes our question. The speed of light, c, ceases to be a physical speed limit in the traditional sense. Instead, it becomes a processing limit. It's the maximum rate at which information, the bits of reality, can propagate through the cosmic network. It's like the clock speed of the universe's computer. The causality it enforces is simply the rule that one calculation must finish before the next one that depends on it can begin. This perspective opens up a fascinating and subversive possibility. If we live inside a computational system, could it be possible to find exploits? In computer programming, a hack or a glitch can allow a user to bypass the intended rules of the system, creating shortcuts or achieving impossible results. Could there be hacks in the universe's fundamental code? Could faster-than-light phenomena be achieved not by applying more force or discovering new particles, but by finding and exploiting loopholes in the way reality is being rendered? This idea is, of course, purely speculative, but it's not entirely without a basis in modern physics. Concepts like the holographic principle suggest that all the information contained within a volume of space can be described by a theory on its boundary, much like a 3D hologram is encoded on a 2D surface. This hints that our perception of a 3D universe might be an emergent illusion from a more fundamental, lower-dimensional code. If we could learn to manipulate that underlying code directly, we would be moving beyond the realm of physics and into the realm of what might be called cosmic engineering. It suggests a future where our descendants might not be explorers in the traditional sense, but reality hackers, learning to rewrite the rules of the simulation they inhabit. Our journey now takes us to the furthest frontiers of theoretical physics. Two ideas that stretch the very limits of our imagination. Our everyday experience is of a universe with 3 dimensions of space length, width, and height, and one of time. But what if this 4-dimensional space-time is just a single, thin slice of a much larger, multidimensional reality? This is a core concept in theories like string theory and M-theory, which propose that the universe may have as many as 10 or 11 dimensions. So, where are these extra dimensions? The leading idea is that they are compactified, curled up on a microscopic scale, far too small for us to see or interact with directly. But even if they are small, they could still offer a path. To understand this, we return to a classic analogy. Imagine an ant crawling on a large, flat sheet of paper. The ant lives in a 2-dimensional world. To get from one side of the paper to the other, it must crawl the full distance across the surface. Now, imagine we fold that piece of paper, bringing the 2 distant points very close together in the 3rd dimension. The ant, still stuck on the 2D surface, still has a long journey. But if that ant could somehow learn to burrow through the paper to take a shortcut through the 3rd dimension, its journey would become almost instantaneous. This is the promise of hidden dimensions for faster-than-light travel. The speed of light may be the absolute limit within our specific room of the cosmos. Our 4-dimensional membrane, or brain, in the language of M-theory. But true faster-than-light travel might be possible by taking a shortcut through these hidden higher dimensions, often called the bulk or hyperspace. By momentarily exiting our brain, traversing a short distance in a higher dimension, and re-entering our brain at a distant location, we could effectively travel between 2 points faster than a beam of light confined to our dimensions. This remains one of the most speculative ideas in all of science, and we have no experimental evidence that these extra dimensions exist. But it offers a breathtakingly elegant solution to the problem of interstellar travel. It suggests that the vastness of space might be an illusion of our limited perception, and that the universe possesses a hidden topology, a secret network of pathways that could one day turn the stars from distant points of light into accessible destinations. For all this talk of grand theory, you might think these ideas are confined to blackboards and supercomputers. But we are living in a golden age of experimental physics, where scientists are no longer just theorizing, but are actively beginning to probe, and in some cases, even manipulate, the fabric of spacetime in the laboratory. We are taking the first tentative steps from science fiction towards science fact. One of the most striking examples is the Casimir effect. First predicted in 1948, This effect demonstrates that empty space is not empty at all. The quantum vacuum is a roiling sea of virtual particles constantly popping in and out of existence. If you place two uncharged metal plates extremely close together, they will be pushed towards each other by an invisible force. This force comes from the quantum vacuum itself. The tiny gap between the plates restricts the types of virtual particles that can appear there, creating a pressure difference between the space outside the plates and the space between them. The Casimir effect is real, measurable, and it provides the first tantalizing hint that we might be able to engineer the vacuum, the very energy of empty space that might one day be harnessed for concepts like warp drives. At the same time, researchers are creating exotic new These are not materials found in nature, but are artificially structured substances designed to have properties that defy our normal expectations. They can bend light in impossible ways, creating invisibility cloaks that guide light around an object as if it weren't there. While a long way from warping spacetime, this work in manipulating electromagnetic fields is teaching us the fundamental principles of how to control the fabric of reality at a local level. In other labs, physicists are creating laboratory analogs of black holes, using everything from supercooled fluids to powerful laser pulses. These dumb holes analogs, for black holes that trap sound instead of light, allow scientists to test the bizarre physics of event horizons right here on Earth. By pushing matter and energy to their absolute limits with impossibly powerful lasers, they are probing the quantum vacuum, trying to coax real particles out of the empty space. These experiments are turning the abstract concepts of general relativity and quantum field theory into tangible engineering challenges. We are standing at the threshold, learning the language of the cosmos, not just to observe it, but one day, perhaps, to write our own sentences. Our journey so far has been one of physics and mathematics. But challenging the cosmic speed limit takes us beyond science and into the realm of philosophy. It forces us to ask a profound question. What does it truly mean for something to be impossible? Throughout human history, the boundary of the impossible has been a constantly shifting frontier. Just a few centuries ago, the idea of powered flight was considered a physical impossibility, a foolish dream reserved for gods and angels. The notion of instantaneous global communication, of speaking to someone on the other side of the planet as if they were in the same room, would have been indistinguishable from magic. Sending humans to the moon was the very definition of an impossible goal. Yet, these perceived impossibilities have become the everyday realities of our modern world. They were not overcome by breaking the laws of physics, but by deepening our understanding of them and engineering clever ways to work within them. The cosmic speed limit feels different. It feels more fundamental, more absolute. It has profoundly shaped our psychology as a species. It defines our sense of cosmic isolation, painting a picture of a universe where the stars are beautiful but fundamentally unreachable, separated by gulfs of time and space so vast as to be eternal. We feel a deep sense of loneliness, confined to our tiny, fragile planet in an incomprehensibly large cosmos. To challenge this limit, even theoretically, is therefore not just a scientific pursuit. It is a profound act of rebellion against this cosmic loneliness. It is a declaration of hope. It forces us to reconsider the very nature of our existence. If causality can be bent, what does that mean for free will? If the past is not immutable, what does that mean for our understanding of time? Pushing against the light barrier forces us to confront the boundaries of our knowledge and our imagination. It is an act of redefining our place in the universe, of transitioning from passive observers to active participants in the cosmic story. Where do these revolutionary ideas from warp drives to hidden dimensions actually come from? They rarely emerge from rigid, step-by-step calculation. Instead, The greatest scientific breakthroughs often arise from a place that feels much more like a dreamscape, a state of profound intellectual play. Albert Einstein is the ultimate example of this. His theories of relativity were not born in a laboratory, but in a series of famous thought experiments or he imagined what it would be like to ride on a beam of light or to fall in an elevator with its cable cut. These playful, imaginative scenarios allowed him to see the universe from a completely new perspective and unlock its deepest secrets. This is the true engine of discovery. The journey into seemingly impractical, impossible concepts, like faster-than-light travel, is not a waste of time. It is an essential exercise for the human mind. It stretches our capacity for wonder, and radically transforms our perception of what reality is and what it could be. When we seriously contemplate what it would take to build a warp drive, we are forced to engage with the frontiers of general relativity and quantum field theory in a way that dry textbook problems never could. When we wrestle with the paradoxes of tachyons, we deepen our understanding of causality. This process reveals a beautiful and often overlooked truth. The most abstract and seemingly impractical scientific investigations are often the ones that lay the groundwork for the most practical and revolutionary technologies of the future. The abstract mathematics of the 19th century, once considered a purely intellectual pursuit, now underpins everything, from our GPS systems to our digital communications. The bizarre world of quantum mechanics, once a philosophical puzzle, is now the foundation of modern computing and is paving the way for quantum computers that will reshape our world. The dream of faster-than-light travel is the ultimate catalyst for innovation, pushing us to ask the biggest questions and, in the process, to discover answers we never thought to look for. As our journey unfolds, a surprising pattern emerges. The universe, it seems, speaks not just in the cold, hard language of mathematics, but also in poetry. Listen to how physicists describe their most profound theories. They don't just call them correct. They call them beautiful or elegant. Einstein's equation E equals mc, in its stunning simplicity, is seen as beautiful. The standard model of particle physics, while complex, is praised for its elegant symmetries. The theoretical physicist Paul Dirac, one of the founders of quantum mechanics, once said that it is more important to have beauty in one's equations than to have them fit experiment. He reasoned that if the equations were truly beautiful, their experimental verification would surely follow. This suggests a deep and mysterious connection between our human aesthetic sense, our appreciation for harmony, symmetry, and simplicity, the fundamental structure of reality. Why should this be? Why should a universe of mindless particles and cold, physical laws adhere to principles that we find beautiful? This implies that beauty itself may be a reliable guide to truth. When a theory is convoluted, messy, and ugly, it often turns out to be wrong or incomplete. When a theory is simple, elegant, and beautiful, it very often turns out to be right. Viewed through this lens, the search for faster-than-light phenomena becomes more than just a technical or engineering challenge. It becomes an artistic practice. It is a cosmic conversation where we are learning to appreciate the harmony between the intricate workings of our own minds and the magnificent, elegant architecture of the cosmos. The Alcubière drive isn't just a clever solution. It's a beautiful idea. The ER equals EPR conjecture isn't just a useful hypothesis. It's an elegant unification. In seeking these truths, we are like cosmic poets, trying to find the words and symbols that best capture the sublime beauty of the universe we inhabit. As our exploration draws to a close, where do we stand? In any simple, practical sense, the speed of light remains undefeated. No particle has been accelerated past it, and no message has been verifiably sent faster than it. The opera anomaly served as a humbling reminder of science's necessary rigor. And yet, everything has changed. Our understanding of the universe has been irrevocably transformed. We have journeyed from the solid ground of experimental physics to the dizzying heights of theoretical speculation. We've seen that the cosmic speed limit isn't the simple, rigid wall we once imagined. It is a subtle and porous membrane, with loopholes and exceptions woven into the very mathematics that describe it. We have discovered that the universe is far more nuanced, bizarrely interconnected, and wonderfully responsive than we ever thought possible. Through quantum entanglement and the ER=EP conjecture, we've glimpsed a reality where distance may be an illusion, a universe stitched together by hidden connections. Through the theoretical elegance of warp drives and the possibility of higher dimensions, we've seen that the vast emptiness of space might one day be tamed, not by brute force, but by cleverness and a deeper understanding of the rules. The universe has not shrunk, but our sense of what is possible within it has expanded beyond measure. We find ourselves not at a dead end, but at a precipice of new beginnings. Armed with a renewed sense of hope and a profound wonder about our place in a cosmos that is filled with extraordinary possibilities, still waiting to be discovered. Let's allow ourselves one final moment of speculation. Let's imagine that tomorrow, a genuine, verifiable, faster-than-light breakthrough occurs. What would happen? The consequences would be immediate, profound, and would ripple through every aspect of human civilization. It would trigger a complete and total paradigm shift, forcing a recalibration of almost everything we know. On a practical level, our technology would be thrown into chaos before being rebuilt on a new foundation. GPS satellites, which rely on the precise timing of signals traveling at the speed of light and accounted for by Einstein's theories of relativity, would instantly become obsolete. Our entire model of cosmology, our understanding of the Big Bang, the expansion of the universe, and the distances to faraway galaxies would have to be re-evaluated. But the technological revolution, as massive as it would be, would pale in comparison to the transformation of human consciousness. Our sense of cosmic isolation, that deep-seated loneliness that has haunted humanity since we first looked up at the stars, would dissolve overnight. The stars would no longer be poetic symbols of the unreachable. They would become potential destinations. The discovery would be a definitive answer to the question, are we alone? Not by finding aliens, but by giving us the means to go and look for them. It would reshape our religions, our philosophies, and our art. It would force a new understanding of our place and purpose in the universe. Such a discovery would be a turning point in human history on par with our ancestors first harnessing fire, the invention of agriculture, or the moment we first stepped off our home planet and onto the moon. It would mark the beginning of a new chapter in the human story, the dawn of our interstellar civilization. It's easy to dismiss the exploration of faster-than-light travel as an esoteric, impractical fantasy with no relevance to our daily lives. But this misses a crucial point about how progress works. There is a powerful, though often unseen, connection between the most abstract theoretical research and the most transformative, practical innovations. The mental flexibility required to even contemplate these ideas, to imagine warping the fabric of space-time, to visualize tunnels through higher dimensions, to wrestle with the paradoxes of time travels, the very same engine that drives all scientific and technological progress. This kind of thinking, which pushes against the boundaries of the known, is a muscle. And when we exercise it on grand cosmic problems, it becomes stronger and more capable of solving problems in seemingly unrelated fields. More directly, the tools, mathematics, and technologies developed to probe these cosmic mysteries inevitably find their way into our everyday lives. The particle accelerators, designed to test fundamental physics, have led to new medical imaging and cancer therapy techniques. The complex algorithms developed for astrophysics are now used in financial modeling and data science. The quest to build more sensitive detectors for faint cosmic signals has driven innovation in our global communications networks. The journey to the impossible is never a waste. Our most impractical questions, the ones driven by pure curiosity and a sense of wonder, very often yield the most practical and unexpected rewards. In our final moments of reflection, we can see that our journey has been about so much more than just physics or the dream of interstellar travel. It has been an exploration of potential, both the universe's and our own. We have seen that the cosmos is a place of profound subtlety and breathtaking interconnectedness, where the lines between the possible and the impossible are not fixed, but are constantly being redrawn by our own understanding. The speed of light still holds firm as the law of our corner of reality. But our investigation has revealed a cosmos that is anything but simple. It is a universe rich with hidden pathways, deeper laws, and tantalizing possibilities that lie just beyond our current grasp. We are not prisoners in a rigid, unchanging reality. We are participants in a grand unfolding story, a symphony of possibility that is still being composed. And the most beautiful part is that our own curiosity, our courage to ask what if, is the key that will unlock the next chapter of reality. We are left with a sense of immense hope and wonder. The universe is not a closed book. It is a library of infinite stories, and we have only just learned to read the first page. The journey continues, and the greatest discoveries are still ahead of us. So, I leave you with this question to ponder. If we did discover a way to travel faster than light, where is the first place you think humanity should go, and why? Let me know your thoughts in the comments below. Thank you so much for joining me on this incredible journey to the edge of reality. I hope you're feeling as inspired and full of wonder as I am. Until next time, please take care, be well, and don't forget to subscribe for more journeys into the amazing and the unknown.